that when I did the following tutorial. I forgot to put the shape names in, but my concentration was on the polarity arrows and the intermolecular forces. So we also need to put in the shape names, and I forgot. On the other hand, it did save some time because I forgot. Just for starters, I would go and write this on your paper or maybe even on a separate sheet of notes. Intermolecular force types from strongest to weakest. Ionic means that it's plus or minus. Overall, it's an ion. The formula has a plus or a minus charge in it. Then there's hydrogen bonding when H is bonded to O or N or F. That's the next strongest. Next strongest down. I mean, this is weaker than that. Strongest, weakest. The next one down the strength chart would be dipole-dipole, which is when there is a 0.5 difference or greater in the electronegativity values, and we call that a polar molecule. I will show you this. I would just write this down. It'll make more sense in a moment. That's polar. And the weakest one would be London dispersion forces. There was a Dr. London. It's not named after the city. I thought it was for a long time, but it turns out there was a Dr. London. Dispersion means spread out, of course. So this is the weakest. And hopefully you've seen the video as to why they're the weakest, because they're just temporary, very, 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 very temporary concentrations of electrons on one part of a molecule or the other. So everything can have LDF. And when you say no, no, no in that order, I would go strongest to weakest. When you say no, 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 the final answer that anything could have is LDF. Everything can have their electrons moving to one side or the other. So if it has a no on these three, well then its strongest force is the weakest one, the weakest possible one, LDF. So I'm going to do some examples here. And the classic is water, and that's what Kendall on the video did, is water. So first we're going to do the Lewis dot diagram. I'm going to put O, H, H, and according to your periodic table, H is a 6 valence, hydrogen is a 1. That means we get 6 and 1 and 1, that's 8. So I take 1 from the hydrogens, right, and put 2, 4, and then I notice, oh, I'm going to need to complete these bonds. So I put 5, 6 from the oxygens, and I share those pairs. And then there were some other notes I might need. Is it a plus or minus? Do I need brackets? No. Did I have to share equally in different directions? Is it a resonance structure? No. Is it an octet violation? No, because hydrogen has 2 valence like usual, and oxygen has 2, 4, 6, 8, so no, it's not. There are no more notes to make in our old version. Now, though, we're going to do this. What are the electronegativity values of these two? So you're going to grab this chart. You can use this chart at any time, and I don't have these memorized either. So we have 3.5 versus 2.1. So is the difference between them 0.5 or greater? Remember this? Is it 0.5 or greater? Yes, it's 1.4. Okay. So on a scale of 4, a difference of 1.4 is actually pretty large. So what that means is that the oxygen atom being a 3.5 and hydrogen being a 2.1 is going to pull these electrons here toward itself a good bit. You don't have to write these numbers in the future if you don't want to. This is going to go that way, and this one's going to go that way. And notice they both went sort of up-ish. So did they spread out equally? Did they go in opposite directions, or both exactly in, or both exactly out, or something? No, they both kind of went up. So the next question is, all right, is this a polar molecule? Well, does it have what they call a dipole moment? Is there a plus side and a minus side to this? And what you're going to do is mentally see if you can find a way to draw a line through the middle so that you can make a plus side and a minus side. And we said these pairs are going to shift up, and basically what's going to happen too is that this cloud that was like this maybe is going to go even bigger because it's getting pushed away by these electrons coming in. And if we mentally draw a line here, and you can draw the line if you want, but you don't have to. You just have to know how to do it mentally. I can say, you know what happened is everything shifted up-ish, because these went up, and this side is a little bit minus, and this side is a little bit plus, and it's going to stay that way because the number values for these from this chart are not going to change. So this is going to be permanent, and this side's going to be a little bit minus, and this side's going to be a little bit plus, and that is a polar molecule. And what we do is we draw a little diagram. We say the negative side is, well, toward the O. If you drew your water molecule the other way, then we would draw it down. But anyway, toward the O side, toward the negative side, or to the point. And we're going to put a little plus sign on our arrow and say that's the positive side. So the answer for whether this is polar is to draw the arrow. If it's polar, and the difference is 3.5, and you can find a plus side and a minus side by drawing a line through the middle, then it is polar, and we draw the arrow toward the minus side. And some college classes would probably actually mark you off a little bit if you didn't put the plus little arrow, plus sign on the arrow tail there. So what kind of IMF does this have? Is the overall charge plus or minus? No. Go to the next one. Does it have hydrogen bonding? Is H bonded to O or N or F? Yes. H is bonded to O. So the strongest bonding this has is hydrogen bonding. And that's your IMF answer, your intermolecular force answer. On oxygen, we get 6 and 6, and I'm going to skip ahead a little bit and make this a little bit faster, and that's the Lewis diagram we get. You might want to hit pause and figure that out. So, is it an octet violation? No. Is it a resonance structure? That is not a resonance structure, by the way. And is this plus or minus overall? Do we need brackets? No. So there's our previous answer from our previous work. Now, is this a polar molecule? Now, you could check this chart, but there's no real point, because no matter what this value is, even if you don't know, you know the difference is 0, because any number minus itself is 0. So can the difference be greater than 0.5? Obviously not. So this is a non-polar molecule. And most people just put NP and don't draw an arrow for non-polar molecule. So we decided all the polar part, so let's go through our IMF. Is it plus or minus overall? No. Does it have hydrogen bonding? It doesn't even have hydrogen. Is it dipole-dipole? Is it a polar molecule with a difference of 0.5 and all that? No. So we're down to our final choice. Everything can have LDF. Is this molecule's strongest interaction between its own kind, if you get it next to its own kind, going to be LDF? Yeah, its strongest version is going to be LDF, because we said no, 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 and we're stuck with the weakest one. That's all it has is LDF. So my intermolecular force answer is LDF. So on N, and I'm going to skip ahead a little bit, we get a triple bond, and one more time, is it a resonance structure? No. And remember, not every double or triple bond is a resonance structure. So no. Is it an octet violation? No, it's not, because that's an 8 and that's an 8. And is it plus or minus? No. All right, so we just leave it. What's our strongest intermolecular force? Is it plus or minus? No. Is it hydrogen bonding? Doesn't even have hydrogen. Is it dipole-dipole because it's polar? No, it's non-polar, right? Because the difference has to be 0 and is not over 0.5 on the figure from here. So the last one you can have is LDF again. So when it doesn't have hydrogen and it doesn't have plus or minus and it's non-polar, the only thing left is London dispersion forces. That's all it could be. Let's do Ni. So let's see. N is a 3, 4, 5, and iodine is a 6, 7. So we have a 5 and a 7. Notice those are both odd numbers. So how about we point one, the odd one from each at each other, and then I get 4 more here, and then I get 6 more here. Now nitrogen is not happy having 2, 4, 5, or 2, 4, 6, I should say. Let's make that a bond. It's going to get grabby, so we're going to steal one from the iodine and put it in here. All right, so now we have something that works, and everybody has 8, and everybody's pretty happy. So let's double check again. Do we need brackets? No, it's not minus or plus. Is it a resonance structure? No. Is it an octet violation? No. All right, so now we can do our polarity answer. What's the polarity, the EN value for N? 3. What's the EN value for I? 2.5. Is the difference 0.5 or up? Yes. Toward which one? The stronger number. Which one's that? The N. 3.0 versus 2.5. And if you want, you might even just write in a 3.0, 2.5 if you want. You don't have to. And so these bonds are going to shift that way. You could draw that in if you want to. You don't have to. And actually, what we're going to do is we're going to very definitely, though, draw a polarity arrow toward the stronger side. There. In fact, I think I'll erase that one, so it's not confusing. Why are there 2 arrows? So we draw the arrow toward the negative side because this side's going to be a little bit negative because these shifted that way. That's the stronger side at 3.0. It's a minus. This side's going to be a little bit positive. And by the way, this little character here is delta. Maybe you had like an ambitious middle school teacher who said, triangle is delta and it means change. Okay, yeah. Also though, triangle is a Greek letter and that's why we call it delta. It's the letter delta. And the lowercase version is like D with a hook on it. So just like G and G don't look alike, well, these don't look alike. But this is the lowercase version. So I don't know if it's supposed to be funny or what, but this has become a little bit of change because it's the little version of delta. How cute. But it is permanent. So this will be the minus side and this will be the positive side. And so our polarity arrow points toward the left, toward the negative side, and I put a little plus sign on my arrow. So what's our IMF answer? Is the whole thing in the formula plus or minus? No. Is it hydrogen bonding? Doesn't even have hydrogen. Is it dipole-dipole because it's polar? Yes, it is. That's why I drew the arrow. And so the strongest intermolecular force here is dipole-dipole. Let's try NO2 minus NOO. I'm going to skip it and say nitrogen is a 5 and that's a 6. And we'll skip ahead to that. And so we go 2, 4, 6, 2, 4, 6. And then nitrogen is a 5, but I get an extra 1, which makes it a 6. So how about we go 2, 4, oh no, whoops. 2, 4, 6. And I'm out of electrons. But nitrogen is not going to sit there and be a 6. It's going to get grabby, but the choices to choose from are equally attractive. And when the choices are equal, it chooses equally. So what we have is a resonance structure. So I'm going to pick the left side just because I feel like it and grab one of the pairs. It doesn't matter which one. Double bond with it. But really it's half a double bond here and half a double bond here. So I put resonance structure. And I will accept resstr for space considerations. Oh, look, it's minus, so minus brackets. And is it an octet violation? Not anymore, it's not. Not when you're really done, it's not. Okay, so what about the IMF? Is it polar? Well, let's look at this. What's the value on N? 3. And oxygen? 3.5. So if you want 3 and 3.5, okay. If you want, you don't have to write those down. So these bonded electrons are going to flow more toward the stronger number. So everything's flowing downward in general. And if I make it a little imaginary line here, I get the plus-ish side and the minus-ish side. And so this is polar toward that way, toward the negative side, and this will be the positive end. However, here is the classic mistake that I make. I go, oh, polar, and I put dipole, dipole. No, let's be careful and let's run through this. Strongest to weakest. Is it ionic? Is the overall formula plus or minus? Yes, it is. So the strongest intermolecular force this is going to have is ionic bonding. How about SiF4? SiF, F, F, F. And F is a 7, so let's go 2, 4, 6, 7. In all cases, you might want to hit pause and get this done and just skip ahead on with me. And then silicon, it's important. I keep doing, oh, silicon. No, silicon, right? I know. I get it wrong sometimes. Silicon is a valence electron count of 4. So we have 4 bonds to complete. So how about we use 1, 2, 3, 4. And I'm out of electrons, and everybody's happy with their 8, and we are done. Do we need brackets? Is it plus or minus? No. Is it a resonance structure? There was no sharing at all. No. Is it an octet violation? No, it's not. So that part is done. And you know what? Here's where the molecular chart comes into play. What shape is that? Because you'll see what I mean. That's a tetrahedral shape. F, 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 Si. 4 bonds, and no extra clouds on the center point. So this gets a little tricky, so pay attention. If we have the fluorines equally spaced in 3-dimensional space around here, it doesn't matter what the difference is. The difference could be 100, which is ridiculous because it can't be 100, but it could be 100, and we would have minus, 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 equally spaced in all directions. And there would be no way to find the plus side. No matter where you draw your little line through the middle, you can't find the side with a partial plus on it. And by the way, I know kids do, I'll do this. Well, this has more minus than that. No, this is still partially charged minus compared to the Si. There's no way to find the side that has the partial plus. Everything is a partial minus. All the outer sides, all the corners are partial minus no matter where you draw that line. And if you can't find both a plus and a minus side, it is nonpolar. I would write that down. For it to be polar, there must be a plus side and a minus side. Both. So I know that we can go and look at this chart. So why don't, but we're going to end up with nonpolar, but we can look 4.0 and 1.8. Oh, that's a huge difference. I know it is. However, this is very minus, very minus, very minus, but it's very minus in all equally spaced directions at the same time. And there is no plus side to this molecule. Therefore, it is nonpolar. And now we can do our IMF question. Is it plus or minus in the formula? No. Does it have hydrogen bonding? Doesn't even have hydrogen. Is it dipole-dipole? We just said it's non-polar. This is only for polar molecules. So all it has left is LDF. How about OF2? O, F, F, and I can see where this is going, so I'm putting the F's down a little bit, or you can put them up a little bit. Anyway, so we get a 6 and 2 7s. So how about we go 2, 4, 6, 7, 2, 4, 6, 7, and then I get 6 more from the oxygen. So I'm going to do 2, 4, and 5 bond, 6 bond, and I know that looks a little lopsided, but there we go. Yeah. Okay. So, does it need brackets? No, the charge is not minus. Is it a resonance structure? I didn't have to share anything, much less equally. No. Is it an octet violation? No. So that's done. Is it polar? Ah. Okay. First of all, is it symmetrical? Is it the same on all sides? No, because look what we have is 2 bonds. And remember, a lot of people would draw this as clouds. I think it's more helpful if you put clouds, the 2 electrons in there. And so what we have there, 2 bonds and 2 clouds, is a bent molecule here. And so it's pretty obvious that if you drew a line here, you get some very different sides. So is there a way to draw the line through the middle where you don't get the same sides? Very much yes. So will it matter about the values on this chart? Yes. What are the values? 4 and 3.5. And maybe you want to write those in. Doesn't super matter, but maybe it helps. So is the difference 3.5 or greater? Yes. Can I find a plus side and a minus side? I can, because the electrons will flow toward the greater number, and so more or less they will be going down. This is downish and this is downish, and it really is the one side because I'm saying that they would flow toward this half and away from the O in the middle. So what you get is an overall flow of electrons that way. And now if I draw that line, I get a plus side where they ran away from and a negative side that they shifted toward. So I get a polar molecule that is polar toward the fluorines. Now, if you drew your fluorines to the top, then draw the arrow up. My point is not that the arrow goes down, it goes toward the bigger number side. The bigger number side if the difference is 0.5 or greater. The difference is 0.5. So I will draw my arrow toward the greater side number. Now, I also want to say that some kids who haven't been paying attention in other years, they come in halfway through this because they've been goofing around and they try to find the formula, right, the pattern, and they go, oh, the arrow goes away from the clouds. That's not the point. That is not the point. The arrow goes toward the side that was greater. If this was 4 and this was 3.5, I'd have to turn the arrow around because everything would have shifted toward the O. This time, everything shifted toward the F. This time, it shifted away from the clouds. Other times, it might shift toward the clouds. So this is polar. So what's our IMF answer? Is the formula plus or minus? No. Is it hydrogen bonding? Doesn't even have hydrogen. Is it dipole because it's polar? Yes, it is. So it's dipole. And then somebody says, but you said everything has LDF. Yeah, but we're going to name the strongest one. And this one beats LDF. So, I mean, we could put LDF on everything, but it's kind of not very helpful because everything has LDF. So, forget it. We're just going to name the strongest one. For instance, I want to do one that I just remembered. I want to do ammonia, which is NH3. And so we get H, H, H. You know what? I'm going to do it the way I would probably do it like this, NH3. And H is a 1, so I guess I'll put a 1 here. And N is a 5, so how about I use 1 here, and 1 here, and 1 here. And I only use 3 for my nitrogen out of the 5 that I get, which means I have an extra pair. So I get an extra unshared pair on nitrogen. I like to put them at the top It doesn't really matter. There's no top to a molecule. If you put them somewhere else, good. But it's on the nitrogen somehow. So, do we need brackets? No. Is this a resonance structure? There was no sharing. Is it an octet violation? 2, 4, 6, 8? No. Okay. So, is it polar? Well, probably. And then somebody says, no, the H's are in all directions. No, what we really have is this. 3 bonds and a cloud. Which means I can mentally draw a line here and get a side that is very different from the bottom. This top, if we're going to call that the top, top is very different from the bottom, very different. So the question is, how different is N from H on this? N is 3.0, H is 2.1. And if you want, you could put 3.0, 2.1. So everything in the bonds will be flowing toward the N, which again, back here, means in this view, they would be flowing sort of up-ish. And you know what's going to happen? These are going to flow, all 3 of them, up, and then they're going to whiz around here more time than usual. And then this cloud is going to get bigger. And what we're going to get is a side that's more minus than usual and a side that's more plus than usual. And so this time the arrow is going to go toward the cloud. And that was my point from before. The arrow does not always go to the cloud or away from the cloud. It goes toward the side with the greater number, as long as there's a side that is actually plus and actually minus. This is not symmetrical. It is not the same on all sides, because I can have a cloud side and a atom side. Everything flowed up toward the cloud, so my arrow will go up toward the cloud this time. And remember, these H's were not really spread around like that. Really, they were angled kind of toward each other like this, because the cloud takes up this space here. So I understand that you may draw it like that, and I don't want to argue about that, but you have to recognize that this shape is really this shape. And as a matter of fact, I've been forgetting the shape names, so it's trigonal pyramidal. And what about its IMF? Is it charged overall? No. Is it hydrogen bonding? Yes, it is. It is really tempting to say, oh, look, it's polar, therefore dipole. Go through the list. Is it ionic? No. Is it hydrogen bonding, which is H on N or O or N or F? Yes, it is. It's H bonded to N, huh? So the real answer is the strongest bond